Welcome to the Explainer. You know that feeling when you're typing away, right? Before you even finish a line, boom, a helpful autocomplete suggestion just pops right up. Or maybe a little red squiggle appears, warning you about a syntax error before you've even thought about hitting save. We completely take this magic for granted, but today we're going to pull back the curtain. We're revealing the hidden architecture that makes all of this possible, diving into the invisible protocols running behind your absolute favorite code editors.
So how exactly does VS Code understand your code before you even hit save? It's a fantastic question. When you're using something like VS Code, Eclipse, or IntelliJ, it really feels like the editor is just intimately familiar with your programming language. It feels like it actually knows Go or Python or TypeScript. But here is the massive illusion at the heart of modern development. It absolutely doesn't. Your editor is actually completely blind to the meaning of your code.
Okay, let's dive into this. We'll be looking at 1. The Smart Editor Illusion, 2. Handshakes and Capabilities, 3. Document Lifecycle, 4. Hovering to Debugging, 5. Domain-Specific Breakpoints, and finally, 6. A Graceful Shutdown. Let's get to it.
Section 1. The Smart Editor Illusion. Who does the work?
Let's look at what's actually happening when you open up a project. The reality here is a very strict separation of concerns. Your editor is essentially a highly optimized but completely dumb UI client. It knows how to render text, manage files, handle buffers, and track exactly where your cursor is blinking. And that's basically it. The real heavy intellectual lifting, that's done by a totally separate background process called the language server. Think of this as the genius brain. The language server is what parses the code, builds the abstract syntax trees, checks your types, and resolves symbols. So the absolutely crucial point here is this. It's tempting to think the editor itself understands the language. It doesn't. And honestly, this separation is arguably the greatest architectural triumph in modern developer tools. Why? Because it completely solves the M times N complexity problem. Think about it. If you have 10 editors and 10 languages, building custom intelligence for every single combination means building 100 separate tools. Nobody wants to do that. But by standardizing the communication between the UI and the brain, every single available IDE, whether you're rocking VS Code, NeoVim, Emacs, you name it, can leverage the exact same language servers. You literally only need to write the language logic once.
Section 2. Handshakes and Capabilities. Establishing Boundaries.
So how do these two completely separate entities start talking to each other? You can kind of think of it like an awkward first date, where boundaries and skills have to be clearly established before anything else happens. The very second you open a project, a 3-step initialization and capability negotiation phase kicks right off. Step 1 is process startup. The editor spawns the language server asynchronously in the background. Step 2, the editor sends an initialize request. This is basically it's saying, hey, here is the workspace, and here are the UI features I support, like auto-completion and hover. Then step 3, the server fires back a capability response, outlining exactly what language features it can handle. Both sides shake hands on what they can do, which ensures the editor never asks for a feature the server just can't provide.
Now, all of this negotiation happens over JSON RPC. What is that? Well, it's essentially a language-agnostic transport format. It's just a transport layer that carries the language server protocol, or LSP, messages back and forth using asynchronous requests and notifications. And what's really brilliant about this is that because it's completely asynchronous, the language server can be crunching massive amounts of data in the background. We're talking running deep static analysis or indexing thousands of files. And it does all this without ever freezing up your editor's user interface.
Section 3. Document Lifecycle and Updates. Push-based updates.
All right, handshake complete. Now it's time to actually start writing some code. The language server protocol relies on this really cool continuous push analogy for its document lifecycle. See, the background server never actually checks your hard drive or pulls the file system to see what you're up to. Instead, the editor pushes the state to it in real time. When you open a file, the editor sends a did open notification with the full content of the file. As you type, it sends did change. When you close the tab, it sends did close to end the act of editing. And did save? That's just an optional trigger for disk-oriented stuff like formatting.
But notice how modern editors handle performance here, because this is key. If your editor sent the entire file to the server on every single keystroke, it would be a colossal waste of bandwidth. We're talking prohibitively expensive and inherently laggy. No one wants to code like that. So instead, it uses incremental updates. It only sends the exact text range that was affected. So if you just deleted 3 characters, it only sends those 3 deleted characters along with a strict version number to make absolutely sure the sequence of edits stays perfectly in order. This highly optimized workflow is exactly why your typing feels incredibly instantaneous.
And this brings us to a really fundamental rule of this entire architecture. The editor pushes the truth. The server uses those lightning-fast incremental updates to maintain a complete, totally up-to-date document in its memory. Even if the code sitting on your actual hard drive is completely different or even syntactically broken, the server always reasons about the in-memory version that you are actively editing.
Section 4. From hovering to debugging. Targeted code requests.
So we've talked about how the editor pushes state to the server in the background. But what happens when you, the user, actively ask a question? Let's say you hover your mouse over a function to see its documentation. The editor doesn't actually look up the docs itself. No way. It simply forwards your cursor's literal X and Y coordinates directly to the language server via a hover request. The server then looks at its in-memory abstract syntax tree, finds the symbol at those exact coordinates, fetches the docs, and sends the text right back. The editor just takes that text and renders it in a nice little box on your screen. And the exact same delegation happens for code completion, or when you use GoToDefinition to locate a declaration across your workspace. The editor delegates all the thinking. It merely renders the answers.
Section 5. Domain-specific breakpoints. Debugging complex DSLs.
Now, understanding code is one thing, but what about debugging it? Standard languages use the Debug Adapter Protocol, or DAP, which is essentially like LSP but designed specifically for debuggers. But what happens when you're working with a highly complex domain-specific language, or DSL? Well, this brilliantly illustrates the solution. For standard general-purpose languages, regular DAP is absolutely great. But for a DSL, we need something a little more tailored. Researchers have actually developed this elegant pipeline that drops a configurable interactive debugger right between the IDE and the language runtime. It bridges the gap using two extended protocols, CDAP and LRP.
So what is CDAP? It stands for the Configurable Debug Adapter Protocol. See, standard DAP just assumes your language has typical everyday concepts, things like lines of code, standard variables, and threads. But a highly specialized domain-specific language might not have any of those things. CDAP is a clever reinterpretation. It adds configuration services, which allows an IDE to interface with a runtime based entirely on the specific logic and unique rules of that specific domain.
To put that into perspective, think about a standard state machine diagram. In a normal language, you'd just slap a breakpoint on line 42 and call it a day. But in a domain-specific language, like a state machine, lines of code don't even make sense. Thanks to CDEEP, the runtime can map breakpoints directly to abstract domain states. You are literally placing a custom breakpoint on the actual concept of transition B to A, or on the event of entering state D. The debugger actually understands the domain itself, not just the text. It's a real game changer.
Section 6. A graceful shutdown. Orderly process cleanup.
All right, so you've written your code, you've debugged your custom domain states, and now it's finally time to close up shop. To prevent your computer from just bogging down with zombie processes and nasty memory leaks, LSP uses a very strict two-step termination sequence. First, when you close the editor, it sends a shutdown request. This basically tells the server, hey, stop accepting new requests, finish up whatever parsing you're doing, and safely release your file buffers and caches. Then, once the server acknowledges that orderly cleanup, the editor sends a final exit notification, which terminates the process immediately. It's a remarkably clean end to a very complex coding session.
So what does this all mean? We've seen how the UI is entirely 100% separated from the brain. The editor itself does literally none of the thinking. It just beautifully renders whatever the language servers and debug adapters tell it to, which leaves us with a pretty fascinating thought. As these background protocols handle increasingly complex reasoning, abstracting away more and more of the actual development environment, what exactly is the future of the code editor? Will the whole concept of a standalone editor eventually disappear entirely, just replaced by thin rendering clients connected to massive centralized intelligence servers? It's definitely something to think about the next time you see that helpful little red squiggle. Thanks for joining me on this explainer, and keep exploring the systems hiding right there in plain sight.